Let's talk now about GANs, Generative Adversarial Networks. So when we look at this, generative means we're actually generating something. So this is a creative process. So we have a neural network that is going to be actually creating new things. Images, text, sounds, music, things like that. And the adversarial networks shows we do have, the plural says we have more than one network. So we're going to actually have a generator and an adversary. How can this be used? So this is used, for instance, in generating fake celebrities. So these are some examples of images that were created from a network. So these are not real humans. These are instead images totally generated from a neural network. So this is a neural network that in some sense is trained to create celebrities. Another example, this is a network that was trained to generate pictures based on a textual description. So the textual description is this small bird has a pink breast and crown and black primaries and secondaries. And these are the sorts of pictures that were generated, which roughly capture this description. So how can this work? A key here is these generative adversarial networks, we have no labeled data. So there's good parts about having no labeled data, right? One is labeling is an expensive process. We've talked about ImageNet and the fact that ImageNet labeling was done with these mechanical Turks, these Turkers. So paying them money to go ahead and take images and put them in one of 1,000 different categories. That's an expensive process. Expensive, labor intensive. Instead, the only images we need are positive images of the class we're interested in. For the first example, what we'll need are examples of celebrity images. In the second case, we will need some examples of images with captions. But that's actually fairly easy to do. We could just scrape the net perhaps, and there's lots of images and captions out there. Similarly for celebrity images, there are a lot of them out there. I'm going to describe this process with an analogy. So let's say you are trying to create a fake ID. Okay, so you're trying to generate a fake ID. But you don't know the first thing about generating a fake ID. So you just generate, I don't know, something that looks like this. You just blank piece of paper, perhaps. And you take that to the bar you're trying to get into, and the bouncer looks at the fake ID and determines whether it's real or not. So we're going to have a discriminator, in our case, the bouncer. Now, are bouncers actually trained to detect fake IDs? I mean, I'm guessing in the vast majority of cases, the training is very minimal. Instead, they're just used to seeing a lot of IDs, and they see a lot of real ones, and they also see some fake ones in there. So you bring your generated fake ID into the discriminator, the bouncer. And the bouncer says, nope, this is not a real ID. But this is a friendly bouncer in some sense, because you are allowed to say, well, how might I make it better? Normally, bouncers are not going to tell you what's wrong with your ID. They're just going to say, no, it's no good. But the bouncer says, in your case, for instance, it's blank, and they say, there's normally writing on it. So you come back, and you try generating your fake ID again. And you go ahead, and you put some writing on it. AXVL2. Okay, random characters, because you are a pretty stupid fake ID generator. Okay? You're just not very good at it. You've never even seen an ID. You don't even know what an ID is. All you know is it's supposed to be, an image this big. And so you heard that you were supposed to put in text. You put in some text. You go to the bouncer. The bouncer says, nope, no good. Well, how might I make it better? Well, let's see. These are normally names. Oh, okay. I'm going to go ahead and generate a different fake ID. So you go through and you put in a name, like, I don't know, McLovin. Right? You come, you go, the discriminator says, not so fast there. This is not a valid ID. Oh my goodness, what now? There's often a picture on it. Okay, so you go back, you put in a picture, let's say of a moose. You come in, it says, no, it's usually a picture of a person. You come in and put in, I don't know, Abraham Lincoln, and so on. And it just goes back and forth until eventually you've got the semblance of a pretty good fake ID. That's the concept of what's going on. This generator doesn't really know anything about what it's generating. All it's doing is getting feedback as to not only whether it successfully has created a fake ID, that is, whether it successfully fooled the discriminator, but it also gets the information of how could it have improved its fake ID? What could it have done better to generate the fake ID? So we're going to have this generator. And this generator is a neural network. So it's a neural network. And let's say it spits out our fake. In this case, it's an image of a fake ID. We need inputs. And so we're going to feed in a random vector. And our theory is, if we feed in different random numbers, we get out different fakes. So, we might feed in 100 random numbers and get out one fake, and then we change some of the random numbers and we get a different fake and different fakes and so on. So except for the stochasticity, let's say, of dropout or something like that, the neural network doesn't have randomness in it. So our randoms that we're feeding in is via these vector. So this gives us some different values for our fakes. The discriminator, though, as well, remember we've got this bouncer, but this is a neural network as well. Okay, so this neural network is our discriminator. This is our generator. And the discriminator gets fed in one of two things. It gets fed in either a fake or it gets fed in reals. So it can get fed in a fake, it can get fed in a real. And the discriminator's job is to come up with a yes or no answer. Is it a fake or is it a real? This neural network to begin with is a pretty crappy discriminator. This generator to begin with is a pretty crappy generator. But we're going to co-train them so that the discriminator gets better and the generator gets better. So the discriminator gets better at distinguishing reals from fakes, and the generator gets better at fooling the discriminator. As the discriminator gets better, the generator has to be generating better fakes. As the generator is generating better fakes, the discriminator has to get better and better. You can imagine if we had a bouncer, right, and we had extremely good fake IDs, they might have to be, using a magnifying glass and looking in a UV light and some other, tools and looking and carefully looking up in a manual of information that they had kept about, for every state, what are the particular characteristics of the IDs there. This book that they have, though, is not a book they bought. This is a book they carefully created with their vast experience of reals and fakes. So as they saw more and more, let's say, Florida driver's license, they wrote down, the expiration date is in the bottom left corner. And then if they suddenly see some expiration dates in the top right, they can say, no, we think those are fakes. If it turns out they're real, then it's going to be learning because the discriminator is going to go through backpropagation. So if we feed in a license, a Florida license where the expiration date is at the top right, and it has said it's actually a fake, then as we go through the backpropagation, that may affect this conceptual updating of information about Florida driver's licenses. So we have G. incoming to G is Z, which is a random value. So we've got a gate here where we can either get inputs from G or we can get inputs from the real. If we have an input coming from G, then the discriminator is going to be trained to learn that that's a no. If we have an input coming from the real, it's going to be trained learning that it is a yes. And then how does this work? Well, basically, what happens is we're going to go through a training process kind of like this. Okay? So we are going to initialize G and D randomly. That is their weights, right? And then we're going to go through a process of train D for a while with what? With random reals and random G of Z's. Okay, that is, we've got a collection of reals. We're going to go ahead and pick randomly from there. And for G, the way we get a variety of different fakes is roll different dice for these Z's, so come up with different random vectors for Z's and feed G into those. When we talk about training, of course, what that means is we're doing backpropagation to update the weights of D. So once we've done this process, then what do we know? We know D is now better. Better at what? Better at distinguishing reals from the types of fakes that G is currently generating. So now D has taken a step up in terms of its improvement with respect to G. And now what do? Now we train G. How do we train G? We pick a random Z, we calculate D of G of Z. Okay, so D of G of Z is basically feed Z into G, feed G into D, and see whether D says yes or no. Actually, D is not really saying yes or no, right? D is really outputting something between 0 and 1.0. Let's back up a second. What's D's loss function? Right, D's loss function, as we're doing its training, is just going to be, so it's going to be our standard binary cross entropy. So standard binary cross entropy loss, where the reals come in with a 1 and the random G's come in with a label of 0. And so it's trying to be generating closer to 1 for the reals and closer to 0 for the G's. Now we train G, we pick a random Z, and we calculate D of G of Z. And now we need to come up with a loss function. What is our loss function? Well, basically, the closer that D is to outputting 1, right, the closer this is to outputting 1, the better of the job we did. And the closer it is to 0, the worse a job we did. So we can use a loss here of, so if it's a 0, we want a very large loss. And if it's a 1, we want a very small loss. So let's think about that. What is the log of these, right? The log of 1 is 0, and the log of 0 is, well, the log of some very small number is negative a very large number. So what we can use is minus loss of D of G of Z. So that should give us a very large number if D is outputting some number close to 0, and a very small number if D is outputting a number close to 1. So we are training based on how well we fooled the discriminator. If we can get the discriminator to say 1, we don't have to have much change to our generator. If the discriminator is saying something very close to 0, we've got a lot of change here. Right? We've got a lot of gradient we need to use. So we're calculating D of G of Z, and then the key is, when we do backpropagation, well, we had Z coming in, we make a bunch of transformations, we make some more transformations, and then we want to go back and update. When we're updating, so when we backpropagate to update G, we freeze D's weights. So we've got the loss coming here, back through D. There are changes, certainly. There is gradient to each of these weights in D, but we don't want to use that gradient. That gradient would be saying, how can we convince the discriminator to allow our G to go ahead and pass? That is, how can we convince the bouncer to change their rules such that our fake ID passes? And that's not what we want to do, right? We have different training that we do for B. We don't want to make D worse. And that's what this would tend to do. So we just freeze D and say, okay, D, you are what you are. But as we get our gradient back into G, that's saying, what are the changes we can make to G's weights such that the output of D will be more favorable to us? And that's the training that we do on G. And then we go through this large process over and over again. So we repeat this. Train D for a while, train G, train D for a while, train G, and so on. And so we're making D better, then we're making G better. D better, G better. The part about this is we're making D better with respect to G and our set of reals. We're making G better with respect to D. So we have this coevolution. What is this? The Red Queen in Alice in Wonderland, right? Where you go faster and faster and you can never make any progress. That's sort of what we have in here. This coevolution is, like the coevolution, let's say, of organisms in the environment, right? Viruses and the fights against viruses, right? As each one gets better. Or spam, right? And spam detectors, right? The spam that gets created used to be, in the past, pretty rudimentary spam, and now it gets quite sophisticated. And that's because the spam detectors get better, but then the spam gets better in the detectors and so on. And then once we have trained G and D to the level that we would like, then we can go ahead and just use G to generate things. So how did we get, for example, the random celebrities? We went ahead and just created some random Z's, fed them through G, and then took the output, and that was a celebrity. In the case of the labeled captions, the Z was somewhat different. Instead of feeding in a random vector, instead we were feeding in a random vector along with the words of a caption. Right? And again, where those words are probably indexes into some word dictionary. So we'd feed in the word and the captions, and the real images would also come up with reals and captions. So D was learning not only is this image look like an image, but does this image does the caption accurately reflect the image? So those are the things that it was learning.